Right, let's start with this one. The program for the next few weeks is this, as you can see. It's a topic called post-optimality analysis in linear programming. And what it does is, well, not just because of uncertainty in parameters, but essentially the whole idea is you've solved your LP problem, so you have your final optimal solution and the optimal simplex tableau. And now you want to investigate what happens to the optimal solution if you start changing things slightly in the original formulation. So in the original data, if you start changing some coefficients, or if you start changing some right-hand sides in the constraints, what's going to happen to the optimal solution? And of course, what you could do is change it and then solve the whole problem again, do all the pivoting again, and then change it and solve the whole pivoting again. But what we're going to do is not that, but instead we want to be smarter, because the final tableau, it doesn't only contain the information about what the optimal solution is, but it contains many more different numbers as well. And so we want to use all those other numbers in the simplex tableau to try and work out with less work what is going on when you start changing the values, let's say. And so the listed some things that we're going to be covering. We start here today, hopefully number 2, and then in the coming couple of weeks, probably what? It probably takes quite a long time. Yeah, maybe 4 weeks. We'll cover the rest. Okay. Okay, so the main thing is we worked out in the past 2 weeks what the tableau contains in the following way. So just to check or remind you, what is B? What is B? Well, B is the basis, so all the variables that are in the basis, they come in a certain order. That's important because you want the matrix to be in a certain order of rows. So of course, if you just permute the rows, you get the same basis practically. But for the tableau, it is important in what row and what order they come, because you want the same order of the rows in the tableau. Okay, so we know what B is. What is A?
Decision variables. Matrix.
Oh, decision variables. A is a matrix of the coefficients of all the decision variables in the constraint. Okay, so well, yeah. So we've got the constraints 3x1 plus 2x2 less than or equal to something, and these numbers 3 and 2 and all the other coefficients sit in the matrix A. And what is the little b here? Well, that's the column vector of all the right-hand sides in those constraints. Okay, so so the constraint are ax less than or equal to b in matrix notation. X is all the decision variables as a column vector. A is the matrix that has as many columns as there are decision variables, as many rows as there are constraints. B is the right-hand side. And then we have maximize or minimize Cx. So what is C? C is a row vector of all the coefficients in the objective. And then M is, you put the matrix A and the identity matrix like this. There's a block, there's two blocks. And then, so that's just M, so I shouldn't be making this my usual problem. And then MB is, well, select the columns of M that corresponds to the variables in the basis. Okay, so this is like the tableau. So these are x1, xn, and these are the slack columns s1, sm. And that's so small that you can't really read it, but it doesn't matter. Okay, and the -1 is just the inverse. And this C dash B, that's similar. So C dash is, you put the C and you put a lot of zeros. And again, there are n coefficients in the objective function, and there are m zeros that correspond to the slack variables, because the slack variables are not in the objective, and so you can think of them as being there with the coefficient 0. Okay, so this is just a revision of what we did last week and the week before. Any questions? That should be clear. So now we've reminded ourselves what's going on. I've not printed it in a very smart way, have I? Okay, so we had this example somewhere along the way, and the example somewhere along the way. And what we want to start looking at now is what happens if we start changing the right-hand sides of the constraints. Okay, so for example, so what happens if this 15 changes to 17? What's the new tableau going to look like? Now, the problem is, I messed up with my papers. But okay, so let's look at the tableau as it is here. We've just changed one thing in the right-hand side. So provided that we don't change the bases here, what's going to change in the tableau? B. It's the only thing that changes is B. Means that the only thing that's going to ever change is the val column. We just change the right-hand side, and this stays the same because there's no B. This stays the same because there's no B. This stays the same because there's no B. I mean, this stays the same because there's no B. So the only thing that's going to change is val. Right. Now, notice that whatever is in the valve is this bit here multiplied by little b. Yeah. And what's here is this bit down here multiplied by little b. So what's going to happen is that the valve column will change. Well, it won't. Not only that it will change, but what's going on here is that this valve column is this big 4x3 matrix, including the objective row, multiplied by the right-hand side. Okay? What does that mean? Well, how do you multiply this matrix times 15, 3, 4? Well, the way it works is that if the vector jumps up, and what it means is that you're taking 15 times this column, plus 3 times this column, plus 4 times this column. Okay? So in particular, this is 15 plus 3 times 3, that's 24. 15 times 0 is nothing. 3 and 4, 7. 15 and 6 is 21. And 15 and 3 is 18. Okay, so this is how it works. Now it still works the same when I change the 15 to 17. So what's going to happen is, instead of 15 times this column, I'm doing 17 times this column. So I'm just adding twice this column to the top. Okay. So the new tableau so first, only valve changes. And how does it change? Well, it changes 2 times the S1 column is added to valve. Okay. So the new tableau I should really have brought it pre-drawn. There you go. X1, X2, X3, S1, S2, S3, X2, S3, X1. Okay, so what's going to happen? Well, the valve will go up by 2022, so it'll be 26, 7, 23, 20. And this whole rest of the tableau is the same as this whole rest of the tableau. Yes, I'm not going to copy it. Do you believe me? Everyone's busy, right? That's good. It's time off for me. Any questions? No? Good. So now in this example, there was no legend about it that would say these are constraints, or these constraints come from there being only enough hours or enough material or enough of other resources, as we sometimes have. But if they were, then you would see that if S1 hidden, but so you see that the you can see now that if I increase the right-hand side in the first constraint by 2, then the objective has increased by 2 as well. But the objective is some profit, and it's gone up by 2. And the 2 comes from this 1 here times the 2 increase in the right-hand side. And the example is a bit silly because there are 1s and 1s, so it doesn't really, probably not so good to explain. But you can see that the objective, if I start changing the right-hand side in those constraints, the objective is going to change similarly. So if I change the right-hand side of the first constraint by a little bit, then by 1 times that little bit, this is going to change because of what we've just done. Change it by 2, so by 2 times 1, we went up to 20. Okay, the second constraint, it's similar. If we went from 3 to 5, or 3, let's say 3 to 6, went from 3 to 6, then this would increase by 3 to 21. Okay, so in this sense, these numbers here give you some sort of value of the resource in that example, if it's a resource allocated. Does that make sense? Okay, so for example, if you look at the assignment, which is about, what's it about? Oh, mahogany. Right, so when you solve the mahogany example, then you get some numbers in your final tableau, and each of these numbers tell you how much your profit increases if you increase that particular resource. So you'll get a certain increase in profit for extra square meter of mahogany. Okay, and if that increase in profit is large enough, then it makes sense for you to buy extra mahogany at a larger price. So this is the key to answering the last question in the assignment. But now let's have another example where we'll see another phenomenon. So this is our favorite chess set problem example. Okay. Do you remember that from first year? Making small and large chess sets. Okay. The first constraint was laid in hours. The second was boxwood in kilograms. And the third was some finisher time or something like that. So now, what do I want to do? Aha. So the story is, the fairy tale is that the finisher wants to take some time off next week. So they're only going to work for 22 hours, I think, is what I put. So they're only going to work for 22 hours instead of 31. I'm going to draw this in square paper. So what's going to happen in the tableau? You can try to work it out. Sorry? The values change. Yeah, try to work it out before I do. You'll be faster than me. I trust you. Matrices. You got it? Oh, why not? Okay, so 20. Quite decreasing. Short.
Well, yeah, I know that, but logic would say times the miniature. You can't exactly increase that to compensate. Big product times.
Okay, I'll tell everyone. It's a good question. Have you got anything? That's it. I think it's good, but it's just you're doing it. Yeah, you're doing it. You're doing it right, and it's good that you should finish. Okay, anybody got anything? Well, do I have to do it myself? 156, are you sure? Is it not 156 divided by 3?
Yeah.
Okay. That's what I'm getting.
Divided by 3.
Okay, so it's time to move on. So my way of doing it is, there was 20 there in the valve. I changed the right-hand side by -9, so this is the -9, times the third constraint, so whatever is in this entry here, 20 over 3, so that's 20 plus 60, so that's 80 here. So that's one way of arriving at it. Another way is, which should give you the same value. I'll do it in the second row. So 160 times 160, the first constraint is still 160 times this 0 plus 200 divided by 3. Well, divided by 3 goes to this 1/3. Plus, oh no, minus 44 divided by 3. 22 times 2/3. Okay, maybe I should have been writing it. Well, whatever. I've written it this way. You have to fight now. So that's 156 divided by 3, so that's 52. So you've seen two ways of getting it. One is start with the 20, it's gone down by 9. So I take 9 times the third column and subtract. And the other way, well, which I think is quicker. So 16 minus 27 over 3, that's 7. No. Yes, that's minus 8. What have I done wrong? 72, not 27. That's what I've done wrong. So minus 8. And the objective, I got 920. Without further ado. Okay, so now the question is, why does it go up if the constraint goes down? Okay, so how is it possible? You know, you're reducing the amount of resource, but something is increasing in the tableau. So the first thing to say is this is slack. So it's like you've got this whatever lathe time, okay? And you're not using the full time on it, and now you reduce the amount of another resource. So that means you can produce even less. So you need the lathes even less than before. Kind of one explanation. Okay. But that doesn't explain why the number of small sets has gone up. The number of small sets is going up because the number of the large sets is going down. So you're trading off. You're doing more small sets and less large sets. And that's one. So it can do various things. It's just the way it is. I didn't bring the picture, so I'll bring the picture next week and I'll show you how it works in the geometry of it. However, what's the problem with this? Yes? Uh-huh. So what are you going to do? Not to make a negative. If you want the new optimal solution, what do you need to do? Just make 0? That will help. What do you always do when you see a negative number involved? You don't times it by anything, no. Yes? Another pivot. What kind of pivot? A dual pivot. Yes. So a dual pivot is just like a normal pivot. We said that. But the way you choose your element is different. And so that's exactly what you need. So whenever you have an infeasible tableau like this one, with something negative in the bulb, if you want a feasible one, you do a dual pivot. Okay? How do you choose a dual pivot? Well, something negative, that gives you the pivot row. And then here you're looking for a negative element. If you can't find any negative element, the problem is completely infeasible and there's no feasible solution and there's nothing you can do. But here there is a negative element. There are several negative elements, you use the ratio. But here you just, there's only one. So, you've got an infeasible tableau, you do the dual pivot, X1 row. This is the only element where you can do the dual pivot. And so, you get a new tableau. And the new tableau is not immensely interesting. Got to be here. Well, I hope it's correct. I was hastily preparing this example yesterday. You get this. Okay, the tableau is on Moodle, so you don't have to copy it. It's also in the video. I hope it's recording. Yes. Okay. So just a brief summary. Change the right-hand side. The only thing that changes is the val column. It changes by multiple. If you just change one right-hand side, then it changes, but just the multiple of the appropriate S something column. Otherwise you have to combine them by all the changes that you do to all the right-hand side. And if it so happens that you get something infeasible, and you have to do dual pivoting until you find yourself feasible again. Any questions? Excellent. So let's say this is 31 again. But now, we've already finished changing the right-hand side. The next thing on the list was adding a new decision variable. So why do we need to add a new decision variable? The reason for this is that the company has decided to perhaps start producing a new luxury kind of chess sets. And these new luxury kinds of chess sets need new kind of chess sets. So one of these boxes needs 3 hours of ladling time, 6 kilos of wood, and half an hour, just like the other ones, of the finisher's time. Okay, so what we have now is we want to maximize 15x1 plus 20x2 plus 30. Oh, I didn't say. And the profit is £30 per set. So plus 30 x3. And the constraints are 3x1 plus 2x2 plus 3x3, so that's not equal to 160. And x1 plus, what was it, 4x2 plus 6. x3 is less than or equal to 200. And okay. Of course, this is a small, silly example, so you don't save much time by not pivoting from the start. But if you imagine something that's got 10,000 decision variables and 20,000 constraints, and you want to add a new decision variable, and you don't want to do all the pivoting from the start, especially if you're adding and removing columns very often, which sometimes happens. So what you want to do is, again, start with all the information you have in this tableau and see what the new tableau is going to look like. Now, this is a bit more, perhaps a bit more, well, a bit less obvious than it was before, but what changes in the tableau? Yeah. Was that the start of an answer, or was it just a sound? So how many columns will the new tableau have? One more than before? Yes, we need an x3 column. Now, what we're going to do first is not put x3 into the basis. Okay, so we start with the same basis, s1, x2, x1. And that means that MB inverse is not going to change, because MB inverse only depends on the basic variables. So B is not going to change, the right-hand side going to change at all. So that's not going to change, that's not going to change, that's not going to change, that's not going to change at all. That's already most of the tableau covered. But also, okay, so when you think about what this is, so this is some matrix. Here. This is some matrix MB inverse, which we know because it's not very nice. Which we know because it's here. And this is multiplied by some matrix A. Okay, so what does the matrix A? It has coefficients of the first variable, the second variable, and now this is new, 3, 6, 1/2. From linear algebra, you must remember, if you don't, then shame on you. No, I didn't say that. I'll have to remove it from the video. Okay, so what do you remember? What do you remember from linear algebra? Okay, matrix multiplication, how does it work? if you want the product, first, what's the first element in the product? You take the top row, now multiply by this column, add it all together. Yeah, second row, multiply by. So if you want to get the first column of the product, it depends on this matrix, but only the first column of A. If you want the second column of the product, it depends on this matrix, but only the second column of A. And if you want the third column of this product, then it depends on the left matrix, but only the third column of this matrix of A. Okay? It's key in matrix multiplication. So that means that here in this product, the first two columns are going to be exactly the same as they were in the original tableau, because nothing changes here. So the only thing that you really need to calculate is the new x3 column. Everything else in the tableau stays as it was. Okay, so let's do that then. You can do it yourselves again, because you know what to do now. Why are you laughing? You know what to do now. The main problem with students is that they don't trust me. They just don't believe me when I tell them that they know what to do. Okay, so what's the basis? S1, X2, X1, objective. What's the value? 20, 46, 16. Just copying. Ah, so now. So now you know what to do. No? Okay. MB inverse, that's this matrix. I'll make it green. We need to multiply this because we want the third column here and multiply with the third column of A, which is 3, 6, 1/2. Okay, so we do this times 3, 6, 1/2. So this is it's kind of like when you're multiplying a matrix by a vector. Okay, so when you're multiplying it from the right, it's giving you a column vector, which is a combination of the columns of the matrix. If we're multiplying it from the left, it would give you a row vector, which is a combination of the rows of the matrix. But now we're doing it where the vector is on the right. So we take 3 times this plus 6 times this plus 1/2 of that. So 3 times 1 plus 6 times 1/3 plus 1/2 times minus 20/3. What do you get? minus 5/3. Oh, I've lost the solution. I've lost the solution. No. Oh no, 5/3 plus 5/3. So that's here. And 3 times 0 plus 6 times 1/3 plus 1/2 times minus 2/3. So that's 5/3 as well. And 3 times 0 plus 6 times minus 1/3 plus 1/2 of 1/3. What's this? Minus 2/3. That's simple. So one would be tempted to continue like that. But one cannot continue like that. Because what one has to do is, well, look at this. This bit is this times A, just like this bit is this times A. So this is, we continue like that, like that. However, we still need to add the minus 30 from the new objective. Okay. So we continue like that, but don't forget the minus 30. So here we've got minus 30 coming from the new objective plus now everything is 3 times 0 plus 6 times 5/3 plus 1/2 times 80/3. That's 40 70/3. 90/3. It's minus 20/3, I think. Is this everything? Well, it is and it isn't. It is because we've now completed the tableau with this basis, but what can we see that we don't like? Negative. What does that mean? It's not optimal. So sometimes when you add a new decision variable, the new entry is going to be positive, and then you just, that's it. But in this case, it's negative, so you need to pivot. So just do the usual pivot. What's the pivot element? I think it's this one. In the usual way. So the tableau is now not optimal Okay, and that's simple. Everybody knows how to pivot. So that will finish the addition of a new decision variable, and you get all the new things. Any questions? Well, you've got a homework on changing the right-hand sides. Some nice examples. Yeah, and now you know how to fully solve the mahogany assignment. And that's it. Thank you.